Determine the simplest form of the following powers of I. So ultimately what we want to do here is if I know that I is equal to the square root of -1 and I squared equals -1, let's take a look at what I to the third and I to the fourth would be. So I to the third is really the same thing as I squared times I. So that's the same thing as -1 times I. So that would mean that I to the third is negative I. And then I to the fourth is really I squared times itself, which is -1 times -1. So I to the fourth is 1. That's also the same thing as I to the 0, because anything to the 0 power is 1. And so if I take a look at what I'm putting in this little red bubbly cloud, that is essentially how I can easily do problems 1, 2, and 3, even though it looks quite complicated. So if I have I to the 34th, that's essentially the same thing as saying I to the fourth times I to the fourth times I to the fourth 8 times, because if I have I to the fourth times I to the fourth all the way, that would be the same thing as saying I to the 32nd. And then times I squared. So I to the 32nd is really just I to the fourth, which is 1, times I to the fourth, which is 1, all the way to the last I to the fourth, which is 1. So 1 times 1 times 1 times 1, 8 times is 1. And then we know that I squared is -1. So I to the 34th is really just -1. Now, that can get rather annoying once the numbers get a lot larger, like in number 3, I to the 1,000. So probably the best way to do this is if I notice that 8 times 4 was 32, the other way that I can think about that is that if I have 32 divided by 4, I got 8. Now, why did I choose 32? Because 32 is the number that is closest to 34 that's actually divisible by 4. Well, how can I actually figure that out without doing too much craziness and trying to figure out what's divisible by 4 if I don't really remember the divisibility rules by 4? Well, I can take 34 divided by 4, and if I did this using the uh, the old method I learned in grade school, the division algorithm, I would get 8 remainder 2. So this 8 tells me how many times I can divide 4 into 34, and then there's a remainder. Whatever this remainder is the power of I that's going to be left over. So let's continue with this. I to the 67th, if I do 67 divided by 4, I get 16. 6 times 4 is 24. So I have 16 remainder 3. So that would mean I have I to the fourth 16 times. So I have 16 of these, which is the same thing as saying I to the 64th. And then I have times I to the third. Well, I to the 64th I know is 1. So now I to the third is negative I. So my final answer here is negative I. Likewise, if I have I to the 1,000th, 1,000 divided by 4 is 250, and there is no remainder. So because there is no remainder, that means that I would be I to the fourth or I to the 0. So my final answer is 1. Essentially, what you do here is you look for the remainder when you divide the exponent by 4. And whatever the remainder is when you divide the exponent by 4, that is your final answer. Well, I mean, it's not your final answer, but then you can kind of look at the look at what actually all of these i's mean, and then that can give you the final answer. How do you add, subtract, multiply, or divide complex numbers? The same way you do it with real numbers. Now, there are a couple of caveats. You must treat I squared as -1, and you must also treat I terms and non-imaginary terms separately. So ultimately, that means that you are combining, that should be an M, combining like terms. So let's do some examples. Number 1, 4 minus 2i plus 3 plus 7i. I'm going to combine the like terms. 4 plus 3 is 7. Negative 2i plus 7i is plus 5i. That's number 1. Number 2, now I have 4 minus 2i plus 3 plus 7i. Or I'm sorry, minus 3 plus 7i minus 8 minus 10i. So if I take a look at all of these things, 4 minus 3 minus -8. If I want, and it helps, then I can actually distribute these and treat it like it is a giant plus or minus problem without the parentheses. And that's probably what I'm going to do here, just to make this a little bit easier, because sometimes we forget to do such things. So now I'm going to combine all the like terms. 4 minus 3 plus 8 is 1 plus 8, so that's 9. And then negative 2i minus 7i plus 10i is negative 9i plus 10i, so plus 1i. So 9 plus I is my answer there. Number 3, going to multiply. I will use the distributive property. Negative 2 times 5 is negative 10. Negative 2 times negative 9i is plus 18i. 6i times 5 is plus 30i. And then 6i times negative 9i is negative 54i squared. So I can combine the like terms. And then one thing I have to remember is that I squared is -1. So negative 54i squared, I can replace with positive 54, because negative 54 times -1 is positive 54. So my final answer will be these two combined to be 48i, and then negative 10 plus 54 is positive 44. So 44 plus 48i. If I look at number 4, I get 18 minus 33i minus 24i plus 44i squared. Negative 33 minus 24 is negative 57, so that's negative 57i. And then plus 44i squared is going to turn into negative 44, because 44 times -1 is negative 44. So if I have 18 minus 44, that ends up giving me, well, I'm making this video on a Sunday, and my brain is not all that with it, so I will actually do the subtraction over on the side. I end up with negative 26 minus 57i. Number 5, anytime I do something squared, that's the same thing as writing it twice. So negative 5 minus 12i times negative 5 minus 12i. And then I can distribute. So I end up with 25 minus 60i minus 60i plus 144i squared. These combine to be negative 120i, and then 144i squared is negative 144. So 25 minus 144 is negative 119. And that gives me my final answer on that one. If I'm dividing, I actually don't really want to divide the same way. I mean, I technically could in number 6. I could write this, since this is a monomial in the denominator. Well, monomial is an interesting term for an I, but I could write it as 5 over I plus 7. And then if I knew a lot about exponents, I could say this is 5 times I to the negative 1 plus 7. And then I to the negative 1, I realize is negative I. So that's negative 5I plus 7. But that's not the easiest way to do this based on where we're at as understanders of what's happening. So what I'm going to do is I'm going to multiply the top and bottom of this by I. Once again, this is something that we talked about earlier. This is a FFU. This is a fancy form of 1. So if I multiply the top and bottom by the exact same thing, I'm allowed to do that since it's really just 1. So if I multiply the bottom by I get I squared. And if I multiply the top by I get 5I plus 7I squared. I know that the denominator is negative 1, and now I have the numerator as 5I plus 7I squared. That's the same thing as 5I minus 7. And then if I have the entire numerator divided by negative 1, that changes the signs of everything. So I get negative 5I plus 7, which, note, is the same answer as when I did it the other way. Now, number 7, I need to figure out what FFU I want to use in this problem. I'm going to use what is called the complex conjugate of the denominator. So maybe make a note. The FFU that I want to use is the complex conjugate. And if I have something of the form A plus or minus BI, the conjugate is just when I change the sign of the imaginary part. So if it was a plus, it becomes a minus. If it was a minus, it becomes a plus. And now I distribute both the numerator and denominator. So the numerator becomes 10 plus 15I plus 14I. So that's plus 29I. And then the backside is plus 21I squared. That's going to become minus 21. And now down here, I get 4 plus 6I minus, plus 6I minus 6I. Those cancel out. That's why the complex conjugate is so valuable, because it's going to cancel out any imaginary parts in my denominator, and I don't really want to have any imaginary parts in my denominator. So it's plus 6I minus 6I. Those are going to go away, and then I have minus 9I squared. So now I'm going to simplify this. 10 minus 21 gives me negative 11 plus 29I, and then the denominator, since the middle parts cancel out, I end up with 4 plus 9, and I get 13. So my final answer would be negative 11 plus 29I all over 13. And if I wanted to rewrite that as negative 11 thirteenths plus 29 thirteenths I would be allowed to do that. Problem 8 is going to be very similar. I'm going to multiply by the complex conjugate. That's 2 minus 5I. Remember, all I have to do is change the sign of the imaginary part in the denominator. So now I'm going to multiply the top part out. That's negative 10 plus 25I minus 16I plus 40I squared all over 4 minus 10I plus 10I. So I don't even really need to write it because I know that it should cancel out. minus 10i plus 10i, those go away. And then this becomes minus 25i squared. So when I simplify this, I get negative 10 minus 40, which is negative 50, plus 9i all over 29, since negative 25i squared is 25. And again, I could write this as negative 50 29ths plus 9 over 29i if I wanted to. So either one of these would be an acceptable form of the final answer. Finally, factor over the complex numbers. Remember that if I have something like 9x squared minus 100, I could write that as 3x minus 10 times 3x plus 10. And that would be a pretty easy way to factor that. But we never knew how to factor 9x squared plus 100 before. I'm only allowed to factor that in the imaginary or the complex numbers because there's no way that I could get rid of the middle terms and have a plus sign unless I have imaginary numbers. So in this problem, I can put 3x and 3x, 10 and 10, plus and minus, except I'm missing something. So if I give myself a little bit more space here, and I put in i's, now what would happen if I distributed this out? I would end up with 9x squared minus 30xi plus 30xi. Notice both of these cancel. And then I end up with minus 100i squared, which turns into plus 100. So this can be factored into 3x plus 10i, 3x minus 10i. So my final answer for number 1 would be 3x plus 10i, 3x minus 10i. Number 2, factoring something like this into the complex numbers. Now, if I graphed this, and if I graph number 1, that would be a parabola that has a y-intercept that is also the vertex at 100. So clearly that doesn't have any real roots, and so that's why we have to factor it into the complex numbers. Number 2 is very similar. It doesn't have its vertex on the y-axis, but it has a y-intercept of 10, and it's a graph that looks something like this. So probably the easiest way to do something that isn't the sum of two perfect squares like number 1 is to do the quadratic formula. So x equals negative 6 plus or minus the square root of 36 minus 4 times 1 times 10 all over 2 times a, so all over 2. So x equals negative 6 over 2 plus or minus the square root, that's bad writing, the square root of negative 4 over 2, since 36 minus 40 is negative 4. And then I can rewrite this as negative 3 plus or minus the square root of negative 4 is 2i over 2. So I could get my final roots of this equation would be at negative 3 plus or minus I. Notice that when I get any sort of complex solution or complex root, I always have the complex number and its conjugate. So a complex root is always paired with its conjugate. They always come in pairs if they're roots. So if that would be what the root is, then if I wanted to factor this, I have x minus p and x minus q, where p and q are the roots. So all I have to do is put x minus negative 3 plus I, which is one of the roots, and x minus negative 3 minus I, the other root. So I just take each of these roots and I put them in with where p and q are, and then that would be my final answer.